The first 3 weeks courses have focused on functions, classes, data items, and a model how they're evaluated. In this week, we're going to concentrate more on types, that is the way the compiler sees these classes and functions. In particular, we're going to learn about fundamental ways to abstract and compose types. The principal concept here is type parameterization. Type parameterization means that classes as well as methods can now have types as parameters. The running example for this week is a data structure which is fundamental for many functional languages. That's the immutable list that's built from individual cons cells. Over the last sessions we have seen quite a few different forms of types, from simple types such as int or double to class types such as rational and intset. What we are going to see this week is more flexible ways to express and parameterize types. This is called polymorphism. So, as a motivating example, let's look at a data structure that's been fundamental in many functional languages from the beginnings of Lisp. It's called the cons list. So a cons list is an immutable linked list constructed from 2 building blocks. The empty list, which we call nil, and a cell that contains the first element of the list and a pointer, a reference to the rest of the list, and that is called cons. Let's look at some examples. The list 1, 2, 3 could be drawn as follows. We would have a first cons cell that contains the 1, and a reference to the next cons cell that contains the 2, and a reference to a cons cell that contains the 3, and finally this right field is nil. Here's a somewhat more complicated example, a list containing 2 nested lists. So that could be visualized as follows. We would have here, let's start with a list that contains true and false. That would be the first element of the outer list. Then there would be another list which is 3 and nil. That would be the second element. And then we would connect those 2 lists like that. And we would finally get a nil here. So that would be the list of true, false, and list of 3 here. So you see the general principle. The question now is, how do we write that as a class hierarchy in Scala? Okay, so here's an outline of a class hierarchy that would represent list of integers in this fashion. We would start with a base trait, call it int list, and 2 subclasses, cons and nil. The cons subclass takes a head, which is an integer, the first element of the list, and a tail, which is the remainder of the list, of type int list, and extends int list. The nil class, representing the empty list, simply extends int list. And we will have to fill in the dots here to show what methods are in this class hierarchy and how we would implement them. Note there's one piece of new syntax here. I've written directly val head int and val tail int list. What that does is it defines at the same time a parameter of the class and a field, a value definition in the class itself. So the parameters that you see here are in fact equivalent to 2 fields, head and tail, that are initialized by parameters that have some other name that's not otherwise used in the program. So you can always express the val parameters in this way, but of course val parameters are much more concise, so they are preferred as a syntax form. But there's actually one other problem with our type hierarchy, and that's that it's way too narrow to define only lists with int elements. If we do it that way, we'd need another class hierarchy for double lists and one for a list of booleans and so on, one for each possible element type. So that's clearly not scalable. What we need to do is generalize the definition, and we can do that using a type parameter. So as an outline, what we're going to do is we are going to define now a base trait list which takes a type parameter t. So type parameters are written in square brackets. And that base trait list of t would have two subclasses, cons and nil. Both of them are again parameterized. Also we call their type parameters t. And in the case of cons, we would now have a head element that is of type t, no longer int, but the parameter t, and a tail element that is of type list of t. And cons of t itself extends list of t. The nil class is analogous, so nil of t would simply extend list of t. What we're going to do now is flesh out this hierarchy, adding the necessary methods and their implementations. And we're going to do that using Eclipse again. So what I'm going to do is create a Scala trait, call it list. And the first thing I will do is add the type parameter to list t. We could have any name, but if this is just a single type parameter at play, t is quite common. So what methods should be put into that trait? Well, there seem to be three fundamental ones. The first method is we need to distinguish between whether the list is a cons cell or the empty list. So let's call this method isEmpty of type Boolean. So that tells us what kind of list we have. Second method would be if we have a non-empty list, then we would be interested what is the first element of that list. So that would be head as a method name. And what should its type be? Well, it would be the element type of the list, so that would be t. And finally, the last method would be tail, which gives us the remaining list, and its type would be list of t. Good. Now that we have fleshed out the base trait, let's go to the implementations. First implementation would be the class cons, which takes a type parameter t, and head and tail, as you've seen. And it's an extension of list of t. And what do we need to implement? Well, let's start with isEmpty. In a cons cell, isEmpty is always false, because cons cells are never empty. What about the other two definitions, head and tail? Well, actually we have already implemented them using the parameter names here. So the val head t is actually a legal implementation for the method head t in the base class, and the same holds for the tail value that we have here. Oh, I just forgot we have to put the tail value here in front, because otherwise it wouldn't count as a field and it wouldn't implement. So what that shows is that in Scala, val definitions, so field definitions in classes, are really special cases of methods, and they can override methods and they can implement abstract methods in traits. The difference between a val and a def concerns only the initialization. A val is evaluated when the object is first initialized, whereas a def is evaluated each time it is referenced. So now we have cons. Let's look at the final one, nil. Nil of t also extends list of t. And we have to implement the three methods. What should isEmpty be? Well, for nil that would always be true. What should head be? Well, the problem with head is that we cannot take the head of an empty list. So what we should do is throw an exception. There's actually a handy exception in Java called no such element exception, which we could throw here, and we can give it a message which says, well, you just hit nil.head. Throw new no such element exception. And finally tail would be the same thing. We cannot take the remainder of an empty list, so it would also throw a no such element exception. What is the type of head and tail? Well, you've learned that throw exception has type nothing, and that then is also the inferred type of head and tail. So to be explicit, we could write it like this. And then you also see why that works, because head is now has type nothing. Nothing is a subtype of any other type, including t. So it's perfectly okay to have a head definition here that returns nothing, and that can implement a head abstract method in the trait list that returns a t, simply because a nothing is a t, and nothing is a subtype of any other type. Good, so that was our implementation of lists, which relied on the fact that we could parameterize classes with type parameters. Type parameters are there not only for classes, but we can apply them also to functions. So functions can have type parameters. For instance, here's a function that creates a list consisting of a single element. So we would write def singleton, and it takes an element of the type of the list. And again, that could be any type. So we parameterize here singleton with the type parameter t. And the body of the singleton is that then simply it creates a new const cell. It passes on the type parameter t to say, well, it needs to be a const cell of type t. Its first element is ln, and its tail is an empty list, and it's an empty list of element type t, the same t as the const cell. And if we do that, we can then write singleton, and we can pass the type along. So we want a singleton of type int now, and the actual value should be 1. And that would give us, of course, the singleton list 1 and nil. Or the other one would be the singleton list true and nil. So we can create lists like that by passing in first the type parameter and then the value parameter. In fact, the type parameters are often redundant because the Scala compiler can usually deduce the correct type parameter from the value arguments of a function call here. So, for instance, for the singleton examples, you could also write simply singleton of 1, and the compiler would infer that this is a singleton of type int, simply because it knows that the constant 1 has type int, so int is the best fitting parameter type. And in the same way it could infer that singleton of true has type parameter boolean, because true is a value of type boolean. So that gives a quite significant simplification of notation, where then the types really get out of the way. They're not in your face anymore, but they do in the background what needs to happen. So when I drew data structures like this, then in fact the actual type int and boolean doesn't form part of the data structure. It's not stored anywhere. And that's a principle that affects all of evaluation. So it turns out that type parameters do not affect evaluation in Scala at all. So to use our substitution model, we can simply assume that all type parameters and type arguments are removed before evaluating the program. Otherwise said, types are only important for the compiler to verify that the program satisfies certain correctness properties, but they're not relevant for the actual execution. That's a property which is called type erasure, so types are erased at runtime, and it's a property that some languages have and others don't. So if we look at the camp of languages that use type erasure, then we see Java and also Scala and functional languages such as Haskell, ML, or OCaml. But other languages actually keep the type parameters around at runtime. So for those languages, type parameters would affect runtime behavior. So those languages include C++ and languages in the .NET family, such as C# or F#. So what we've seen here is a form of polymorphism. Polymorphism is a Greek word, and its original meaning was having many forms. So applied to a function, it means that the function can be applied to arguments of many different types. Applied to a class or a type, it means that the type can have instances of many different types. In fact, what we have seen are two principal forms of polymorphisms, namely subtyping and generics. So subtyping means that instances of a subclass can be passed to a base class. So, for instance, in the case of list, I would have two subtypes. One was the class nil, and the other was the class cons. And wherever I would have a parameter that accepts a list, I could pass either a nil or a cons. That would be just as good as a general list. So that means that it's a form of polymorphism, that it could have one of those two forms. The other form of polymorphism we have seen was generics, where we can create many instances of a function or a class by type parameterization. So using generics, we could create a list of ints, or a list of doubles, or a list of booleans. The two forms of polymorphism complement each other well, and Scala has both of them. Typically, you would say that subtyping was traditionally a form that object-oriented languages had first, whereas generics was a form that functional languages had first. So let's do an exercise. Given our definition of lists, write a function nth that takes an integer n and a list and selects the nth element of the list. So we assume that elements in the list are numbered from 0, so the first element of the list has index 0, the second has index 1, and so on. The other specification is that if an index is outside the range from 0 up to the length of the list minus 1, so it's outside range, then you should throw an index out of bounds exception. So let's see how we would solve the exercise. I have here our implementation of lists. What I want to do is create a worksheet on which I could implement this method, call it nth. So I want to import in the worksheet what we have defined in the list class. And I want to define a method, call it nth, that takes an index of type int and a list of type list of, well, we want to be flexible in the element type, so that should be a type parameter of our nth method. And we return an element of type t. So how do we implement that method? Well, one good way to do it would be to ask whether the index n equals 0, and if it is, then we would have the answer immediately. We could just return xs.head, the first element of x. On the other hand, if n is not 0, then what do we do? Well, the idea then would be to say, well, to take, let's say, the third element of a list, that would be the same as taking the second element of the remainder of the list. So we would do an nth of n minus 1 as the index, and xs.tail as the list argument. Okay, so now we have defined nth. Let's test it. Let's do a list. So we have defined the list 1, 2, 3. And let's do nth of 2 and the list. What would we expect? Well, it's 3 because we have arranged that elements in a list are starting from 0. So the one element would be at index 0, 2 at index 1, 3 at index 2. So far so good, but there was another part of it, and that says, well, what do we do if the index is not in the range of the list? So that would be something like that. And here we see a Java util no such element exception, nil.tail. That's an exception, all right, but it's not the one that we wanted. The exercise said we should return an index out of bound exception. So what do we do here? Well, we have to change our definition of nth to guard against index out-of-bound exceptions. So what we need to do is change the definition of nth to take account of this behavior with exceptions. So the idea here is to say, well, if our list is empty, then we can essentially not select any element, no matter what the index. So we have to catch this case beforehand. So what I would do here is I would just say if x is empty, then we throw a new index out of bounds exception. And now we see the worksheet behaves as we want. Nth minus 1 of list will throw an index out of bound exception, and I would hope that nth and 4 of list would do the same thing. Yes, it does. Index out of bound exception in both cases.